Thank you for joining us for this broadcast of Science and the Solar Eclipse. I'm your host, Gordon Dickson. Dr. George Matzko is a research chemist and professor, and he has agreed to join us to talk about what we have learned about solar eclipses. Throughout history, it has been during solar eclipses that we have learned so much about the sun and the stars, about starlight, and about the nature of the universe. Now let's join Dr. Matzko. Thanks again for joining us today. We're on the line with Dr. George Matzko. Dr. Matzko is going around the country. He and Mrs. Matzko together, they're part of the Matzko Science Ambassadors. Am I thinking correctly? That's the name of your ministry, Dr. Matzko.
That's right. And we're a ministry out of Cornerstone Baptist Church in Greenville, South Carolina.
And tell us your website address one more time for those who are listening.
It's my name run together, georgematzko.com. So that's GeorgeMatzko.
And so
georgematzko.com.
We hope you'll reach out to the Matzkos and learn more about it, because these have been fascinating discussions as we have talked about this. One of the reasons that we're having this broadcast and conducting this is that we have a solar eclipse coming on April 8th, 2024. But we also noted there were several more eclipses coming up in the next few years. So we thought it'd be appropriate to put some broadcasts together and talk about this, because so many fascinating things have been discovered about the sun during solar eclipses. And if you go back and look at the history of that, it's fascinating to see how the moon passing over the sun has actually allowed us to study the sun much more carefully. Dr. Matzko, we picked up last time and talked about the nature, basically, of the sun. How does the sun produce both light and heat, and what's the connection between those?
So the sun produces light and heat through a process called nuclear fusion, which occurs in the core of the sun. Only there are the temperatures and pressures high enough to cause this process to occur. So it takes hydrogen nuclei, which are protons. Remember, we're talking about plasma here. The electrons are stripped away. So we have protons that are fused together to form helium nuclei, which we would call alpha particles. And there's a release of energy in the form of light and heat. Maybe you remember the famous formula E equals mc squared.
Yes.
So there is E is the energy that's released. M is the change in mass between going from hydrogen to helium, and C is the speed of light then squared. So the core temperature and pressure, that's the extremely hot, dense region where temperatures reach millions of degrees Celsius. Pressures are immense due to gravitational forces acting on the sun's mass. Then you have a proton-proton chain reaction. So the primary fusion process in the sun's core is 2, or should I say 4 hydrogen nuclei or protons undergo a series of nuclear reactions that form a helium nucleus, which is the alpha particle. So you can summarize this as follows. You have 4 hydrogens, give you 1 helium, plus 2 positrons, 2 neutrinos, and the rest of it is energy that's released. So this energy that's released, again, can be calculated from E equals mc squared. It's released primarily in the form of visible light, infrared radiation, ultraviolet radiation.
And I remember from our earlier discussion that this understanding of the sun is not actually that old in the history of the Earth. I mean, it was during one of the solar eclipses that they discovered the presence of helium for the first time as a new element that they, if I understood you correctly, they hadn't even discovered on Earth yet.
That's right. So Arthur Eddington was the one who first proposed the sun and stars derive their energy from nuclear reactions in the core. But you think about 1920s, I mean, he was pretty precedent about that as far as being able to figure that out.
He's one of the ones we want to come back and talk about on a future broadcast, because he's one of the ones that measured and actually precisely measured what Einstein had actually predicted. And so we'll save that for another broadcast. But Eddington
I'm
was
kind of blown away that he was able to figure that out in the 1920s.
yeah.
Anyway, so think of the sun as four layers. At the core, where the nuclear fusion occurs, you have temperatures reaching around 15 million degrees Celsius. Okay, you have to have these high temperatures and pressures for nuclear fusion to take place. Then you have the photosphere, that's the visible surface of the sun that emits the sunlight. It's got an average temperature of about 5,500 degrees Celsius. Then you have the chromosphere, that's above the photosphere, which is the layer of the sun's atmosphere, and its temperatures can range between 4,000 and 10,000 degrees Celsius. And then you go to the corona. Now, this is interesting. The corona is the outermost layer of the sun's surface atmosphere. Its temperatures can reach millions of degrees Celsius, much hotter than the photosphere. And the exact mechanisms of why it does that and how it does that is subject to much research and debate. There's some theories, but nobody's quite sure how the sun works. So one of the theories is a magnetic reconnection. The idea is the high temperature is a result of complex magnetic fields interacting in the sun's outer atmosphere. So we have to understand that some of the energy isn't in the form of magnetic fields, and the way they interact with each other could actually heat the corona of the sun. Other theories are wave heating, nano flares, wave turbulence, particle acceleration, wave damping, non-thermal heating mechanisms. Anyway, there's all these theories. We don't know how it works. You know, I was thinking about this in terms of the Earth. There's a theory called, I'll call it a paradox, called the dim young sun paradox. That's not a Chinese guy. This is dim as in not dim as far as
not
being bright.
Yeah.
Not bright, and young being young, not old. Okay. And if you think of the sun starting off as a ball of hydrogen primarily, as secular scientists would think of it, you would think that hydrogen fusion is going to be less energetic than helium fusion. And so we would expect, as the hydrogen is used up and more helium is produced, that the sun would actually become hotter. That is, the Earth would receive more energy from the sun later than earlier. That's not a problem for those of us who believe that the Earth and the sun are just thousands of years old. It's a real problem for people who believe that the solar system is actually billions of years old. Because you would expect, as you would dig down on the Earth, see what the climate was like on the Earth years ago, you'd expect things to be colder in the past, maybe even 30 degrees colder. But that's not what we find. Generally we find things look warmer in the past. And so there's something wrong either with the way we think the sun works, or in this idea of deep time. That is the sun and the Earth being billions rather than just thousands of years old. So the dim young sun paradox is actually not a paradox for young Earth creationists like me. It's a paradox for secular scientists who can't figure out how this thing works.
And I remember reading that it was during an eclipse that they figured out that outer layer was actually hotter than the inner layer.
That's right, because during the eclipse, because the sun and the moon are the same size in the sky, you can actually see that outer layer of the atmosphere of the sun, isolated from the other parts of the sun, and they could actually measure its temperature. So that must have been a real surprise the first time they figured that out.
Yeah. Talk about wanting to go back and check your notes and think, well, how could that possibly be? And yet this is part of the mystery. And it's as if, we talked about this in a previous broadcast, it's as if because the moon is passing over the sun. Am I thinking correctly? Do I remember the sun
That's
is
right.
400 times the size of the moon, but the moon is
That's right.
400 times closer than the sun. And so you have two of the roundest objects in our solar system. And so the moon passes over the sun, and it gives us the remarkable opportunity to actually study what we're seeing there.
Yes.
Proverbs 25, isn't it? Around verse 2, he talks about it is the glory of the Lord or the glory of God to conceal a thing. And I often think about eclipses that way, that's one of the things we're learning in a process like this.
But this whole idea about, how you have this 400 ratio, how the sun is 400 times further away, but it's actually 400 times larger. And so the moon and the sun appear the same size in the sky. That's only from the surface of our planet,
right.
Surface of the Earth. And there's no other planetary system that we know about, either in our solar system or in any other solar system, exoplanets, where standing on the surface of that planet or moon, we can actually see the sun of that planet the same size as the moon of that planet. Yeah. It's only here. It's unique to our particular situation.
And yet it was in learning about the composition of the sun that actually taught scientists a great deal about the stars and how the stars actually function and what they were actually composed of.
Yeah. I think there's still a lot of mystery in how the sun works. We really don't understand it. I often talk about climate change and global warming. People are interested in that. And they want to know, what's going to happen in the future. Do we have a warmer future ahead of us? Do we have a colder future ahead of us? I know there's been some scientists that have said that we're going to go into a minimum, that when the sunspots disappear, that actually gets colder on the Earth, as it did back in the Monner minimum back in the 1680s, when the Thames froze over and crops failed and millions of people perished because of famine. Terrible time. We call that the Little Ice Age. And so some scientists say we're facing that. In other words, we're going to have a whole generation of colder than normal temperatures. Others say, no, we're going to have global warming, and it's going to get warmer than it has been in the past. And when people ask me to make a prediction about that, I say, well, we don't understand the sun. If we don't know about this 11-year cycle of sunspots, we don't know how the sun really works. So we're really just taking baby steps here, trying to understand how the sun works. Like this whole question about why is the corona so hot compared to other layers of the sun? We just don't know.
Well, it really fills us with wonder. And I'm hoping that a new generation of young people will take up the challenge here and say, hey, I'd like to study that. I'd like to find out, why that is the case, because it just highlights that all the scientific discoveries have not been made, and there's still a great deal more to learn.
Yes, that's true.
Dr. Matzko, thank you so much for joining us on the broadcast today. When we look to the next broadcast, one of the things we want to talk about is one of the most historic of the solar eclipses and what we actually learned about the nature of the universe from that. So we hope that you'll join us next time. Dr. Matzko, thank you again so much for joining us today.
You're welcome. We look forward to it.
Thank you. These broadcasts are brought to you by LiveServeLead.com. Live, Serve, Lead, helping others succeed.